and then you all create a shot in miraculous time. It takes years to create vaccinations.
Well, it used to take years.
Okay, it used to.
You know how many years were invested in this approach? About 20 years of science.
Y'all campaign is about fear. It's about inciting fear in people. You all attack people with fear. That's what this pandemic is. It's a fear. It's fear, this pandemic. That's all it is.
Today, I want to update you on the next stage of this momentous medical initiative. It's called Operation Warp Speed. That means big and it means fast. A massive scientific, industrial, and logistical endeavor, unlike anything our country has seen since the Manhattan Project. You really could say that nobody's seen anything like we're doing, whether it's ventilators or testing. Nobody's seen anything like we're doing now within our country since the Second World War.
We've got to follow the science.
Under the advice of my attorneys, I will invoke my right under the Fifth Amendment of the Constitution to refrain from answering your questions.
Do you think that the DOJ should reopen the investigation into the AutoPen, specifically pertaining to Fauci?
Well, the only thing you can really think about is the AutoPen, because the most powerful thing the president has, they say, is the power of pardon. So he was pardoned by Biden, and I respect that.
I think we're going to see the proliferation of AI. The other one is 6G. We had made a commitment working with your administration, working with FCC. We're going to accelerate 6G. We're working to have a launch first in the world in the LA Olympics. And I think that's another opportunity for America to lead in the next wireless evolution. So thank you. Thank you for the opportunity. Thank you for the partnership. And we're going to be hard at work, I think, driving that agenda.
So we're into 6G now. I just finished 5G. I was a leader on 5G, getting that done, and now they're up to 6.
Let's do it again.
What does that do? Give you a little bit deeper view into somebody's skin, and now they're up to 6.
Let's do it again.
What does that do? Give you a little bit deeper view into somebody's skin. See how perfect it is. I like the cameras the old days. So they just had a nice feature. Now they cover every little. Let's see, Michael, you're in good shape. You're not gonna. But I tell you, it's the 6 is coming, huh?
It's coming.
Does it ever end? And what happens? You'll be into 7, right? Before 6 gets old, you'll be into 7.
Internal bionano things. These are for the health applications. I did also a lot of research on that the last 15 years. Bio-nanoscale machines, but these are for the injecting into the body and always monitoring the health problems, and that is also really going really well. Like with these COVID vaccines, it's going that direction. These mRNAs are nothing than small scale, nanoscale machines, right? They're programmed and they're injected. And then into another nanoscale things. So those will be part of 7G and beyond, right? So the title is you saw the longer version of it, but the shorter and more technical version is Internet of Bionano Things, and which the terminology I coined back in 2008 with my PhD students, and we did a lot of work the last almost 20 years. And the last stage of this research was or is how to detect, avoid infectious diseases, and that's what I will present you today. And so let me give you a brief background story. Back in 2006, when I was producing 4 PhD students that time, they were on the research market for professor positions, and they all came back and were complaining that all departments in the US were looking for nanotechnology people. And then I got interested to know about the nanotechnology, and I started to study it because I remembered my time back in early 70s, the microchip era, and how much it impacted our lives. So I got interested, I started to work on it. And that time, Fernando Brunetti, the second person and from Madrid, and Cristina Blasquez from Barcelona, the poor lady, young girl, she died recently. And they came to my lab as visiting researchers, and I suggest them to work on these nanotechnologies. And I'm a communications professor, telecommunications. And my interest was more from the communications perspective. And I realized that in the nanotechnology, majority of the work was done on the nanomaterials and also on the nanocomponents of computers. So my interest was more based on communications, and I wanted to know how these devices will communicate when everything is out on the market. So that's why this interest came. And then I realized that there's a perfect communications paradigm in the nature about nanoscale machines, which I will present to you today. And then we realized that also it's kind of like biology-inspired nanomachines. And then also we said we can also create nanomaterial-based, like graphene or metamaterial-based nanoscale machines. And we look at their communications problems. And then those years in 2007, I hired Massimiliano Pirabon, the second guy. And also his name is there too, somewhere, Josep Jornet. So from Barcelona, and then I started the research group. And then in the meantime, we received many projects all around the world. I started a research center in Barcelona, even in Saudi Arabia and Jeddah. So anyhow, so I will present to you. So we also work with some other disciplines like biomedicine and electrical engineering, computer science, physics, etc. So all their names there. So this is the kind of like a list of references. So I mentioned to you, this is the work that BioNano things. As you see here, the human body has all these nanoscale machines inside the body, like neurons, hormones, and calcium signals, and bacteria, molecular motors. And when you are interested in these Nobel Prize, I always say Oscar, Nobel Prize, majority of the people in the medicine are receiving Nobel Prizes within these concepts. So you can check that also. And so these nanoscale machines in the human body are communicating in the human body. And so then, how can we get the information from the inside the body outside, number one. Number two, can we also create nanoscale machines like as neurons, like artificial neurons, artificial calcium signals, artificial bacteria, and then also solve many health problems. So that was our objective. And then also get the information out what's going on through some gateways, which will be on the, outside the body, and then the information will come in and we'll use the internet to go back to the physician's offices. So this entire concept is a closed loop concept. It's called Internet of BioNano Things. So we published one of the first papers in 2015, and then we continue. So I mentioned to you there are two directions. One is the nanomaterial inspired nanoscale machines. You see there that like a perfect computer, like all these components like processor, antennas, memories, and then you see also these brushes. They're zinc oxide nanoscale batteries, but there are also now new battery technologies that they can create this very tiny nanoscale machine. And for the material, the graphenes, which is invented by Gaim and Novoselov, two St. Petersburg Russian people. They got Nobel Prize in 2010. And then the other way is the bio-inspired, meaning can we create bio-inspired, meaning artificial molecules or artificial machines. So again, you will see what I'm talking about when I talk about bio-inspired. So we will be focusing more on the bio-inspired concepts here. So let's look at from the nature perspective. So there are these so-called eukaryotic cells, like human cells, and prokaryotic cells. A typical example is E. coli bacteria. And these are perfect nanoscale, precise nanomachines. And also, they can communicate, interact, and cooperate with each other. Like you see here on the left-hand side, eukaryotic cell tissue, and on the right-hand side, you see bacteria population. And so they are really communicating with each other. There are like billions of them, and then they communicate with each other, and they create like swarm of, cells, or a swarm of, or it's also called in biology quorum sensing for the bacteria population. So let me show you the, inside of these eukaryotic cells. Like you see in the middle, there's so-called nucleus, and there are also ribosomes. They are perfect example for biological memory for the ribosomes, and the nucleus is a processor. And then there are these mitochondria. They are biological batteries, like energy sources for the cells. And there are chemical receptors, there are biological sensors, and molecular receptors, because they are communicating through molecules. And then they're also called gap junctions, and they're a perfect example for transmitters of molecules. So there are, as I told you, millions of them, and they communicate with each other. So let's look at the prokaryotic cell, like bacteria. If you don't like biology, I'm really sorry. Anyhow, so the prokaryotic cells are a little bit mishmashed, not clear like the human cells, eukaryotic cells. They still have these, the nucleus and plasmid, like here you see in the middle, and they are like perfect example for nanomembrane processors. They have also so-called pilies, like they are like sensing, nanosensing units, and also actuating units. There is also cell membranes, which is acting like nanopower unit, like battery, and protein receptors, like nano receivers. Ribosomes they also have as acting like transmitters, and there are these flagellums, like tails. They can navigate them. So this is a perfect example for a bacteria, or especially E. coli bacteria. But I have to say that they are moving very, very slow. So when you look at them under this platform, like they are very, very small, and then when you feed them sugar, they populate, and then when they don't get sugar, they die. Okay, so it's very interesting. So again, just to give some more examples for the mitochondria, which is the biological energy source, battery. So what they do is these mitochondria obtain glucose, amino acids, fatty acids, and oxygen, and they synthesize so-called ATP, or adenosine triphosphate. So just let me give you an example. When you're tired, so you say, I need I need air, right? You go out, you get oxygen. So you charge your mitochondria. Or the doctors tell you, don't feed sugar or chocolate to your kids just before going to bed, because their cells are getting charged and they got a lot of energy, right? So that's a typical example how these cells are charged with these mitochondria. So here's the biological memory and processor. The DNA is in the nucleus, contains the information of a protein structure, like it acts like memory. Since you are in the computer science, you know the Turing machine, right? One-band Turing machine. That's this DNA strain. It's like you can read all these DNA values. And then there are these so-called ribosomes, as you see in the middle. Like the Turing machine read and write things, right? It reads and processes the DNA information and acts like a processor, and they synthesize the proteins, and the proteins control the functionalities of each cell, and for example, cell signaling as transmitter and ligand binding as receptors. So all I'm trying to show you is that these cells, right, as alone, but then they communicate with each other. Like in the eukaryotic cells, as I mentioned to you, we have so-called molecules. Like what are the molecules? Like proteins, ions, and hormones, depending on the nature of the cells. And then they get packed with the messages. We'll talk about those. And then they flow from one end to one cell to another cell. I mean, it looks like long distance, right? It's not. They're all close to each other, right? So then prokaryotic cells, like typical example are the bacteria, like the transmitters and receivers are so-called molecules. As an example, auto-inducer exchange for quorum sensing, meaning these swarm of the bacteria. So now there are these some names in the biology. So now the bacteria comes, and then the transmitter, the cell, puts into the information into this plasmid. It's like into memory. It writes there, and then these bacteria are slowly moving, tumbling around, and then they can also. This is called chemotaxis process, and when they reach the destination prokaryotic cell, they mate. Then it eliminates. Suddenly, you can see that, even with naked eyes, even they eliminate. That means it can put the information sent to that bacteria into the plasmid of that bacteria. So that process is called conjugation. Okay. So as I mentioned to you about also these transmitters, like these cells, for example, release these molecules, right? And so they float. And like as I told you, the gap junction was acting like transmitter. They float, kind of like diffuse, and then they move towards to the destination. And the destination can try to suck those molecules. When they are successful, that's called ligand receptor binding. That means the molecules with the information are received correctly. And so these are kind of like chemical receptors, right? So this is a perfect example for how a transmitter and receiver works inside of the human body, for example. So what we try to do is we try to create this so-called molecular communication theory. You have seen that, transmitter receiver, like wireless communications, and then the channel model here, right? And source creates these molecules. It goes through the channel, and then it's received by the destination. And we try to find out what is the effect that these molecules with the message loaded are received at the destination, what type of effects they will have at the destination. So let me go to these, the way that the communication theory people may know about electromagnetic communication and acoustic communication. They are usually waves, right? Sine waves and etc. And then also in optical communication and quantum communication, we also have these waves as you see here. But in the molecular communication, we are really so-called particles, and they diffuse in the air. They just go to, sometimes they get lost, they don't go to the destination, and some of them are sucked as the ligand binding receptor by the receiver. Okay. Now, after this brief introduction into the biology, the question here is, can we create man-made, man meaning, human-made biological nanomachines? The answer is yes. That means we can reprogram these artificial cells and via DNA manipulations, and that's called genetic engineering. And that will really help us a lot. In fact, unfortunately, some maniacs in the US found all my work the last 18 years. I'm getting a lot of hatred mail, so my life is in danger. They think that I'm Dr. No in James Bond movies, that I'm trying to manipulate human lives, but it's, I'm not the only one. There are many people working on this subject,
Just so you guys know, he's actually talking about my community, mine and Sabrina's community, because we're the only people that are actually talking about this guy and the work that he's doing, and the International Telecommunications Union, United Nations, is doing. He's talking about my community because there's a lot of people out of my community that have been emailing him directly and asking him to explain himself. Like, does he even realize what he's fucking doing here? He does. Anyways, yeah. You're just paranoid people. That's what you guys are. For even considering that this could harm the population.
So now what we try to do is, so you have seen the bacteria, right? So what we can do is we can try to genetically engineer this bacteria, and there are many illnesses, as you know. I will point them out to you, based on bacteria or viruses, right? So if I create genetically engineered healthy bacteria, for example, Crohn's disease, I don't know if you know that, it's an awful disease for intestines. So there's no cure. So I can inject into the body, and then they can fight these ill cells or ill bacteria and then solve the problem, So just an example. So I hope you are getting the point, right? So we are trying to create these nanoscale machines, genetically engineer them. They will act like bacteria, and also in the future we will see that neurons and calcium ions and etc. And it will help us for prolonging our lives. In fact, the mRNA, the COVID COVID injection is exactly based on this idea. So all these fluids, right, there are nanoscale machines inside, right? So when you look inside. So now I want to demonstrate to you there are a lot of nanomachines in the nature, like these eukaryotic cells or cells like neurons. You can see, I will also demonstrate to you all these components like mitochondria, nucleus, and all the other ones that you will see, gap junctions. They are really a nanomachine in the nature, or bacteria on the right hand side. Bacteria has these messed up internal organs, but still, this is much more orderly than the bacteria. But anyhow, that's also a nanomachine in the nature. So now you can see also these nanomachines in the nature, they communicate. On the top, you can see the eukaryotic cells, like 2 nanomachines, and they're using molecules like proteins, ions, and hormones, and pheromones, we'll see those. They communicate with each other through these molecules. And down there, you can see the bacteria are also communicating, as you can see, either as nanomachines, bacteria, and then they have these so-called chemotaxis process. They bind to each other, right? Or they can also do like, bacteria and then release molecules like DNAs or autoinducers, and then they will be captured by the other bacteria. So this is already existing in the nature. So now let's take this cell, the eukaryotic cell that I told you, and look at all these components again, step by step. So you can see there's this nucleus DNA, there are vesicles, gap junctions, receptors, and mitochondria. So now, can we learn from these components, develop these components in our physical world, and then also create this nanomachine which is inspired from the nature, right? So now, here is a very good example for energy sources. So what happens in the cells is, cell gains useful energy. It combines glucose, amino acids, fatty acids, and oxygen. Okay. And then there is this so-called ATP, adenosine triphosphate. That is the energy created for the cells. Sometimes you say, oh, my sugar level is low, my energy low, because the glucose level is low, for example. Now, you can see this under a microscope. It's a mitochondria. I couldn't even pronounce these things correctly. My biology friends told me it's called mitochondria because I was saying different words. So mitochondria. So it's under a microscope. So it's like getting all these amino acids, fatty acids, and glucose and all that, oxygen, and then it creates energy, okay, for the cells. And indeed, this concept is already being used in the, it was even in CNN news last 2 years ago, that there are some concepts already that they are creating the sprays that they will spray on your cell phones or mobile devices, and the mobile devices will gain energy. And it's exactly based on this idea. Of course, don't go and try to find them. They're not there in the market, right? So it's going on. It's not science fiction. Right? So now here is biotransistors. These pictures are from IEEE Spectrum last year. So they had a special issue about this. Like as you can see here, how can we design a cell in the same way we design a silicon chip? Okay? How we can create biological transistors based on protein synthesis from DNA, as you see on the right-hand side. So DNA and synthesis. And then what we can do is we can create these devices which are producing silicon chips, but the silicon chips are hitting these Moore's law ceiling. I'm not an architecture person, but now we can try to create these new chips
as cells, living circuits. And we can expand this capacity of these chips, right? And then, of course, accordingly, they will have much more powerful functionalities than just the silicon chips. That's why we are saying that their capacity will go up. Then, can we also create transceivers? Like you can see, this cell releases these molecules, like proteins, as you can see here, and they're floating around. Can we mimic this and then create a transceiver? And then it will release molecules, kind of like messages, packets, right? And the same thing, the cells are receiving, like these molecules in the nature, and this process is called ligand binding process. Like these molecules are coming, and they will be sucked by the receiver in this case, and that's called ligand binding process. Sometimes they get lost. Okay. So now, can we mimic this as a receiver, and then create our receivers for our machines? So these are question marks. Next question mark is, here is an antenna from a moth. Like, the animals are communicating. They all have antennas, like in the picture that you see here. And the pheromones are, for example, coming, and they will be received by all these like cuticles and all that. And they will be evaluated. It's kind of like receiving signals, and then they will be evaluated by the receiver. So now, can we learn from the nature and then recreate these antennas and realize these nanomachines?
Why you call this antenna?
Which one?
The
no, like this antenna is from the moth. I mean, all the other antennas are also like animals.
It's not an antenna in the way we mean it. It's a chemical communication. Okay.
Exactly.
It's not an antenna.
Yeah, but that's what we are trying to learn, and then also realize it. Can we do the chemical communication in our world? I'm coming to those two, right? But I'm trying to find the bridge. They don't call antenna, but at least that's what in our world it's kind of antenna role, right? And receiving them and evaluating them. Okay. So, and then long term, the next 20 years, I think we will have machines that they will have certain parts from the nanomaterials, from the first part that I explained to you, and second part maybe could be like learning from nature, and they will be put together as a hybrid nanomachine. Like you can see here, like zinc oxide wires, and then biological nanosensing units, and then maybe we can also have the batteries learn from these mitochondria roles. So that will be, in my opinion, the long-term solution, coming up with hybrid components and hybrid nanomachines. Okay. Now what I did so far is I explained to you the components, what people are trying to do. In my opinion, the first track will be faster, like doing all these nanomaterials. The second track will take longer, because it's not easy really to map everything to our physical world, like the nature. So now, once these devices are developed, and they can be used for many, many applications, especially when they are put together and they create these networks. One of the applications is, it's kind of like intra-body nano networks. I mean, now there are these body area networks. I'm not talking about those. We're talking about like intra-body nano networks. Like these nano devices will be injected into the body, for example, into the blood, for example, and they will have zillions of them, like white and red blood cells, and they will be like additional cells, and then they will communicate cooperatively. So there's a nice cooperative communication, and then they will attack the viruses and bacteria, right? So it sounds very science fiction, but that's the reality. And so now, and all these diseases that you can imagine, that they will be history, like all this diabetes, and like Alzheimer's, epilepsy, depressions, and then cancers, hopefully, and then malaria. So the list goes on and on. So that's in the medical field, there will be huge revolution. My opinion is, again, once we solve all of these the next 30 years, and I'm sure the nation will give us other problems in terms of health. So I say that the life human life should be prolonged to 200 years, but I think there will be other problems, so that we will somehow be
I
fighting
think this
this.
famous medical person in England says there's no reason why we cannot meet telephone.
That's right, but I'm a little bit more conservative. I said 200 years. So, but now here is another example that we can learn from this nanoscale communications, like the neurons, the cells, with both electrical and molecular links to other cells. And then we can study those communications of these nanomachines, and then what it will help us for the medical people is they can understand better how in vivo networks of neurons work. And then they can try to create these diagnosis and treatment tools, for example, for brain pathologies. Okay? And then here is another application, like the heart muscle cells, okay, the cardiomyocytes. And they are interconnected for heartbeat synchronization. And they also use molecular and electrical communication. And again, when we learn, understand how these components are communicating, then we can also develop according diagnostic tools and disease treatments. And now here is another world that is called bacteria communication, bacteria. And I did not know this actually. Bacteria are also helping us, by the way. You know, the humans, we all, you know, I'm working with biologists and medical people. So indeed, we all have bacteria in us. But sometimes you go to a country, then you have some problems because you say, I'm not used to your bacteria. So that's a typical case. And we have to have these bacteria. And then the bacteria are, there is this notion called quorum sensing. That's the gigantic cooperative communication. Like collectively, they work, millions of zillions of them. They work together. And what they do, for pollution control, they can be used. Then they can clean residual waters, by the way. And they can also clean pipes. So they have a lot of useful roles that they do. But what we learn from them is, again, bacteria is a nanomachine, and how they create colonies of bacteria, how they communicate, how they do quorum sensing. That's what we will learn as communications people, and that's what we want to somehow apply in our world, right? So now this cooperative network behavior, as I told you, quorum sensing, it's also interesting. There are these man-made machines. One of them is also, like there are these biologists, they take bacteria and engineer them, they program them. Like, you know, synthetic bacteria, for example. And they are programmable. They can be genetically engineered. And they also carry DNA information, and you can somehow guide them, monitor them. Because I will also talk about the project that we have. So we are working with those guys. It's a very interesting world of bacteria. So now another thing here is Internet of Things, or nanothings, right? So now everybody talks about cyberspace and Internet of Things. Now we are also talking about nanothings. You will have inside of our body, outside, there's zillions of these components, machine to machine. They can also be on the nanoscale and having all these nano components. And here, future Internet after that, this is like 50 years down the road, all the machines, I'm 100% sure that all machines will have nano components in them, fully nano components. Nano components doesn't mean that, you know, humans are made of nanocells, nanomachines, right? Well, we're not that small. So in other words, what I mean by that is we can have base stations, normal base, but all components are nano. Or we can have the gateways and switches or mobile devices. They can be all nano components. But what is the gain of it is, remember AI, that was hot topic in the cognitive science in the 80s. How can we create human-like machines, intelligent and all these capacities? And with the nanoscale devices, components, we will reach that. That's why I believe, strongly believe, all these future devices will have nano components in them. And accordingly, the internet and all these mobile, everything will be nanoscale. And then advanced health systems, we talked about it. Just showing another, like e-mobile and mobile health stuff, right? That could be also part of this. And then another thing here is these chemical attacks. when you use microsensors, when you put like this type of environment, and when there is an attack, biological or chemical attack, once they detect it, it's too late already. So you are dead. So because they are not that highly sensitive, highly fine granularity sensing. Where with nanosensors, nanosensing units, you can capture those chemical attacks and alarm them. So these are some examples. Here is this terabit wireless networks. Like how can we operate these terabit per second wireless networks? And that's kind of like 5G, but I think it will be like 6 or 7G. Or here are terabit, kind of like gigabit Ethernet optical link, and then terabit per second links between these devices. And here is another one, like terabit access networks, like this, kind of terahertz wireless access networks. And then here is another one, multimedia kiosks and wireless, very close, short range. You can download zillions of terabytes of data very fast, for example. So these are some examples, but the most driving example is coming from the medical field, as you have seen. That's more exciting. And the other ones, we can always twist existing technologies, but the medical cases are very promising in my opinion. So now let's go back to what we did. As communications people, we try to investigate both tracks, like EM-based and the molecular track. So the EM-based, with Josette, we did this work. We tried to see how these nanoscale machines communicate. And we investigated that, and we ended up in the terahertz. Now, I will also come to your question. So now, we developed this mathematical model and calculated the total path and then the noises. And then we have seen the terahertz band is very unique. It's like 0.1 to 10 terahertz. Okay? Because there are so many channel models, propagation models for the gigahertz and megahertz. They're in the textbooks. Why another channel model, right? So that's why we wanted to emphasize there are some uniquenesses there, right? So now what we did is, I will show you the formula. This is a classical total path formula, total path loss formula, like spreading loss and absorption loss. Spreading loss is the same, but the absorption loss is really showing these peculiarities of the terahertz band. Because here you can see this spreading loss, but the absorption loss, you see all these gases and water vapors in the channel. They do not play a role when you're in the gigahertz level. But when you go to terahertz level, those gases and water particles, they really screw up the signal propagation. And they're all captured in this absorption loss. You can see here, like reference temperature, system temperature, molecular volumetric density of each gas, and etc. They're all captured in this formula here. And then accordingly, we can see that the terahertz band, and then accordingly the noises also are affected by these gases and water particles. So what did we learn out of this uniqueness of the terahertz band and what we learned from it? We have, there's a lot of math, but I skipped those. What did we learn is the terahertz is affected by the presence of different molecules in the medium. And then high molecular absorption attenuates the traveling wave and introduces noise into the channel. Okay. So now here is the picture that we learned, like depicted. Now you can see there is a terahertz band, like from 1 to like 10 terahertz. And these are the distance. Now your question comes, right? So two devices, like 1 millimeter, 1 meter to 1 kilometer. So now you see they are extremely distance limited. So now you can see the red area is like it's impossible. The loss is so high that you don't have meaningful communication, right? But below 1 meter, you have these areas. It's kind of like windows, right? And then you can try to still communicate and have meaningful communication. So they are distance limited. So,
Can I ask a question?
yes.
Because since you are going through different chemical molecules,
I'm not here chemical, I'm talking about EM.
no, the medium is chemical, because it's a physical medium, so it has molecules, right?
Yeah, but in gases and yes, yeah, okay.
Right. So,
But the communication is EM.
it's not, but in other parts of the physics work, people have tried to modify the chemistry to amplify the signal. Okay. So in other words, as I said, the signal, this causes a chemical reaction which actually carries the signal across. Has this occurred here at all, this thought at all?
No, we look at the second part when we talk about molecular communication.
Here you're using the medium that
Yes,
communicates through. One is
we did that in the molecular case. We are just looking at from the chemical perspective, and then we look at all of these in our models. But here we are just saying we want to do classical way of EMs
classical EM.
and a terahertz band.
So this is just an obstacle.
Right,
It's
right.
not used to chemistry. Not
No, I'm just trying to show that can we go with EMs and nanomachines and communication? Yes, we can, but we are distance limited. That's what I'm trying to show.
Because for instance, in underwater communication, right? In underwater
Okay, so what you tell me is it's more my future objective hybrid cases.
Correct. Because in underwater communication, we use that. We use the fact that if I change the salinity,
Okay.
and other properties, I can create long wavelengths.
That's true. And that's another thing that we wiped out the acoustic communication, for example, for these cases. Can we also use that? I don't know, but maybe revisit. But what you're saying is more like hybrid case, that we can do, once I want to understand this, and then the other part I will demonstrate to you after 3 hours. No, but then, we'll see. So we are I'm trying to show you the classical way. In fact, we are also in this interest group of terahertz band, so we present all of that, so it's going well so far. So now what I'm showing you is, this is the case that we learn. What did you learn is, we are very distance limited, and then also the water is the enemy of the water particles, is the enemy in the terahertz band, the biggest enemy. So, but the gain is we have gigantic bandwidth. Like you can have terabit per second easily. So if you try to find a way, as John said, maybe amplifying and all that, to increase the distance, that would be perfect, right? But it's distance limited, like below 1 meter between these components. Okay. So what we did is, this is a commercial now for our work the last 3-4 years. So we did some work on the nanopatch antenna as a design. I will come back to that we are trying to also finish the design and do some experiments the next 3 years. Then this work, the channel modeling capacity analysis, was published in ICC and Transaction Wireless Communications. And then we did some modulation schemes and network capacity analysis for SECON conference. Then we looked at the low-weight channel coding scheme. But the interesting thing here is that we are trying to use avoidance, like, remember the CSMA collision avoidance? Now we are saying, can we also avoid errors before they happen and they try to are detected and corrected? So that's called like low-weight channel coding. We learned it from many, many years ago from the computer architecture. We try to use it here. And then we also developed, by the way, here in the modulation schemes, we developed this time shift on and off keying, T-SOC, with very femtosecond long pulses. It's like learn from ultra-wideband, but these are femtosecond long pulses on and off. But there was another novelty there is, we do not transmit zeros, we just keep silent. And having silence is perfect because we are not using the channel. So we are trying to find an encoding technique that it will take the messages, it will create more zeros than ones. Because keeping silent is better, because then we will avoid all the errors in channel effect. So these are all explained in that paper. And then we have energy harvesting paper, and then my other people in Barcelona, they developed a MAC protocol. Again, all the physical layer effects there. And then we have also nanotransceiver design for the Barcelona people that will appear in ICC. So as you see, these are all design and ideas, concepts. And the objective here is this project Granite. I hope that the government will support us soon. Graphene-based networking, Granite. And we are working with MIT guy, Thomas Palacios is a device guy there, an antenna guy, and also Kyung Oh, he's in UT Dallas. These are very successful people. We have this team. We are trying to, what we want to do is really very simple device here. That's transceiver, antenna, and then another one. And then we just want to look at one-to-one communication the next 3 years. So it's a long way to go, okay? So we want to do prototype, right? So this simple model, and then do all our mathematical modeling, analysis, experimenting with one-to-one, for example. Okay? And by the way, same concept is like under the name grant is by the European community at UPC. So Granite and grant. Okay? So now let's come back to the, some of you say we came here for molecular, you talk about EM. Well, I want to share all of these things with you. So now there is a strong statement, and in fact, I don't take the credit for it. 2000, one of our biology professors, he was acting vice president at that time. He was giving a speech at a dinner table. And I said, what a BS, you know, because he said, the 21st century will be the century of the molecular world, biology world. And all the new inventions will be done in this field. So I was thinking, what the heck are you talking 12 years ago? And indeed, over the years now, after I got into this area, and I strongly believe that the information technology era is coming to an end, like all the empires, right? Look at the Ottoman Empire, Chinese Empire, Greek Empire, Roman Empire, US Empire. So they're all coming, no, really, this is the history, yeah? So the information technology era is coming to an end in like 80 years. It started in the 50s, right? And it will really fade out slowly. And all the new era is the molecular technology era. It already started, but the real wildfire will catch in 2020, in my opinion. So we are still a long way to go, but ideas are there.
Without information, technology, the seven cannot happen. I can put this in writing.
Okay, so we can learn from that. I didn't say it will be wiped out, but in 50 to 100 years, that will be obsolete. Everything will be based here.
Nope.
Okay, we can put a signature and then put it in the history.
It will be called molecular IT, but it will not be.
Okay, but the word is there. I mean, you can also call it, Greek, Roman, what is the empire, but is it still, okay. I mean, I don't care how you call it, but it will not be the way that we are used to this IT.
That's different.
Right, that's what I mean.
So you should say conventional IT technology, or the current IT technology.
That's what I mean.
Clarify.
That's what I mean. Okay, so the molecular communication is a new interdisciplinary field. Okay, now here's another history, and again, we're all timers here, that since 30, 40 years, always they say work together, like NSF, Department of Defense, build teams, and we are in the Mira, for example, right? So, but it never occurs the way that these agencies expect it, because most of the time I say I can do it myself, I don't need the other people. That's really the truth, but here it's indeed an interdisciplinary research. So some of you may be saying, my God, I don't want to learn biology. Indeed, then you have the biology friends and colleagues that you can work with them, or the physics, chemistry, medicine. So it's a truly interdisciplinary research that you need each other and you learn from each other. And I went through those phases the last 5 years, talking to those people. It's very difficult because they have different language and you have to teach each other, but it helps you a lot. Apropos, I hated biology in the high school, but I didn't need to learn biology because I have my colleagues. You know, I asked them about how can you use this in your field. They explained to me, and we explained them the communication aspects. That's why you need them. But if I want to develop an algorithm, why should I get a computer science guy or operation research? I can develop it in my lab, for example, because I know the theory and all that. But there, I don't need to learn all the things again. So that's why it's really truly interdisciplinary research. So now, this is a picture that we keep fixing. The first one was very primitive, but this is like the based on the ranges, like short range, medium range, long range. Okay, medium range is look, nanometer to micrometer distance between these devices. Some of you will say, where can I use it? There is this notion of, I'm not architecture, but in the Barcelona we have a supercomputing center. There is a big guy there, Mateo Valero. So he said, can we create this network on chip multi-cores? Like, they are all close to each other, right? So short is a medium range, and then long range. And then we did this wireless, but in fact they're all wireless. But because they are so close to each other, that's why we call this wired. In fact, in reality, that's wireless. So there are these in the nature again, molecular communication. Molecular motors, ion signaling, like the most important one is the calcium signaling. Then the medium range bacteria like chemotaxis, and then long range pheromones and pollen and spores. And can we learn how these natural communication systems exist and then remimic them in our field? Right?
So where do you put hormonal communication?
Hormonal communication will be all in between, proteins, right?
That's primarily long range, right?
No, proteins are hormonal. It depends again here and then actually here.
Because they use the blood to communicate.
It's here.
They're long.
But they are not. They are still also short, right? They
There
go.
are some, but they are close.
So yeah, they are all here. Okay. Now I have also some cases. The example that you call it like capillaries, for example. They're on this here. Okay, like because it's a long range.
You see,
I remove those because it's too much.
What I don't like this chart, if I may say something.
Sure. Go ahead.
Is this attempt to try to say wire the wire.
That's why it's mentioned that we should remove those. But each time I fix these things. So like I had capillaries. Now you mentioned that I should put it back there, right? Capillaries is really indeed it's a long range, and then there's also this these nerves that right. So it's also long, right? Long range, 1 meter. I had those in one of those slides. So now let's look at these cases very quickly. What is a molecular motor? As you see here, a devil-looking type thing. This is indeed from the microscope. So it has like it moves like 1 step and then 2 step back. So and then there are these microtubules like rails. That's why we call it like wired. But in fact, they are still wireless. The devices. When you look at the big picture like this, like 1 nanomachine here, another one, of course, very short distance, right? These devil-looking proteins or molecular motors, it has this vesicle, it moves very, very slowly. 500 nanometers per second. Talk about delay-tolerant networking. Yeah, it's like funny for computer science people, like here's a delay-tolerant network. And bacteria need 4.5 hours to move 1 centimeter. So it's a real delay-tolerant network. So now you can see, they are moving like that. So what we do is we will create message. That's another challenge. How will we create the message and put it into vesicle, your cargo of this protein, of this nano transporter, right? And then it moves like with these feet on this microtubule, which has 25 nanometers, and then go to the destination. So all of these.
The analogy you described it, okay? Some people will say this is more close to a nano dimension post. I have the carriers and the envelopes.
Yes. Exactly. Right.
It's another metaphor.
Yes. Here's one of the ideas here is, can we use DNA encapsulation and create these messages like you can see there and put them in the vesicles and then transport them? But it's in ongoing research. So if I make, in fact, Tony Ephraimides, he listened to me once in one of his keynotes. He said, oh, you took the same classical way of all the steps. I said, look, we are still learning. So I tried to find bridge to our world. It doesn't mean it must be exactly these here. Maybe not. Well, but we are learning. Somehow I need to tell to communication people, like, you know, these classical steps, right? Encoding. How will we select the right molecules that represent information? Then how will we attach the information packet to the motor in the cargoes, right? And then how will they propagate? Very slow, right? And then how will they be received? In other words, they will be detached, you know, downloaded or detached from those vesicles. And how will they be decoded, right, at the end? So these are all question marks that we need to answer. So you can see that's like one step could be one PhD, for example. It's not that easy for it. Same thing, yes. Same thing with calcium signaling. That's the second portion. Now, how can we encode the information in calcium ions? Now we are in this, you know, chemical domain, right? And then how will we initiate the signaling of these ions? And how will we propagate these calcium waves, calcium ion waves? And then how will we receive them, the concentration, and then decode them, right?
I mean, one
and all decode meaning in this case reacting, they call it reaction.
The answer to Tom's question is pollen, right? The light blue ribbon you have is the symbolic representation of the processes, and the yellows are the physical
Exactly.
and this can differ.
Exactly. Yeah, but I mean, you know.
For the audience here, because we work a lot on cyber physical systems.
Good, so you understand, good.
This can be examples.
I just mentioned that somebody may say, why we are still doing this classical way. That's it. That's why I'm trying to map these physically exactly, and how we may not have all the steps that we do in classical way. I don't know. I really don't know the answers. Now, the problems of this molecular case is that the velocity is 500 nanometer per second. As I told you, it's very, very slow network, so communication. And then also another thing here is molecular motors, when they are longer distance, they detach from these rails, microtubules, you lose them. Okay? The other one is unidirectional communication, and then of course, very, very long communication delay. Same problems with the calcium signaling. So now the bacterial communication, we have this paper that we published in JSEC in May 2010, that is with bacteria. This is E. coli bacteria. So now you see, this could be also mimicked as a nanomachine, like these nucleodes and then the plasmids, the flagellas, and moving around. You can put your messages here, and then you can carry these messages. And it's very interesting. I observed that when bacteria merge, chemotaxis process, they eliminate. There's, you know, you can observe that in the microscope, because there are like millions of these in the colonies. And they're all working in the colonies that, you know, talk about mimos, million by million mimos, right? No, really, it's very, very interesting world. So here is again, the actual steps, and then how we can convert them. So one of the challenges is, how can we create this DNA packets, messages, and then put them into these bacteria cytoplasm? Ideas are like plasmids, bacteriophages, or bacteria artificial chromosomes. And then the transmission, propagation, reception, I put all in the Wander's umbrella, because they look at sense gradients of attracting particles in the real life. And they move towards direction and find more attractants, the process called chemotaxis, where they, you know, merge, right? And then they merge, meaning bind to each other. And the receiver releases attractants so the bacteria can reach it. That's also the distance issue. And then the extracting of this DNA packet from the plasmid using, for example, restriction endonuclease enzyme process. So now, how can we learn all of this and remake that the bacteria case in our world? Plus, of course, all these things about cooperative, like quorum sensing, cooperatively they will work and communicate is a problem, because here we are only looking from single transmitter and single receiver perspective, but there are in reality millions of them, right? So how will we capture those? And here is another example with the long-range communication using pheromones. First I thought like elephants can smell like 20 kilometers, so we said that several kilometers, but then we realized we should be more conservative. It went down to 1 kilometer. Like pheromones, each animal has its different pheromone. Like tigers have different pheromones, and donkeys and elephants and all that stuff. Thanks God to the nature. You know why? Otherwise we'll have a lot of mutant creatures in the world, right? No, seriously. Yeah, so really.
No, because the genetic is not good.
I don't know, but sometimes it happens, you know, in some of the, yeah, but, you know, so only, so, now that's why I said that. How do we select specific pheromones, like kind of the message type, and then transmit the information and produce the reaction and the intended receiver. And then they release the pheromones through liquids or gases, and then they are diffused into the system. And now the reception is called ligand binding receptor process. That's a very complicated process that, you know, again, a lot of losses happens. You don't, you know, bind it to this coming in pheromone, for example, and then decode it, because different pheromones trigger different reactions. So now, when you look at this pheromones from the nature, that means we'll have zillions of MIMOs in and out. Like you can see, like different colors, receptors, blue, etc. That means each of them can receive certain pheromones, right? So where will they end? How many receptors will we have? So that we can create these receivers which can interpret different pheromones.
And they're actually interacting with each other.
Yes, 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 exactly. So now, having told you all these natural phenomena in the communication aspects, now let's go to our domain, the communication domain. What are the needs? So now I always say, who wants to become the new Shannon, right? So can you create a new information theory? Okay. Then I will explain to you some of the challenges there. Now here, all the design and development nanomachines are the domain of the device people, right? We need modeling tools, not only for simulation of the communication, but also for the device people, modeling tools and simulation tools. Normally we all are using like discrete event systems like this queuing theory, queuing models. Here they are trying to use automata theory models. Like automata theory, 1976, I took the classes on automata theory and cellular automata. And I was thinking, I love that, by the way. And then when the cellular automata, it was saying that the machine produces itself, and I was saying, what the crap is it, you know? Self-producing automata, cellular automata. And now, many years, 40 years later, people are using those. Mealy automata, Moore automata, cellular automata, to, you know, model the nanomachines and understand the components, and then also for communication perspectives, right? So it's coming back again. So, and I went back to the Google, and I found that so many results came out in the cellular automata. There was this firing squad synchronization problem. So we can really learn a lot of these from that area. So then other thing is about communication, architectures, like topologies, and also the protocols, communication protocols. Not only just the MAC and routing and all that stuff, but also, in fact, all those steps that I showed you, right? You know, encoding in our language, propagation, reception, decoding, all of the above. Right? Error control, that's an all open question.
Because it doesn't happen in the examples you gave one-on-one, it's many all the time.
Oh, that would be, yeah, right. But my suggestion to the young people to start with one-to-one, you know? Otherwise, that's what we did actually.
That brings the nerve down to everything.
Yeah, so what we did is, we took this, the time is getting short, right? Right, so I will, so this one appeared in JSEC in 2010, but we did a vanilla analysis. Vanilla analysis meaning we don't have anything noises, anything, no problems, right? So simple transmission, diffusion, molecule, and then the reception. You can see here, like, you know, two nanomachines, and all these molecules are floating around, and this is kind of like diffusion process, okay? And then we try to analyze in terms of path loss and delay, for example. But there are many challenges here, you know, like this source behavior, destination behavior, and these particles or the molecules are floating around, right? So what the questions were to answer in the transmitter case: how chemical reactions allow the modulation of molecular concentrations as transmission signals. Then propagation, how the particle diffusion controls the propagation of modulated concentration. And the receiver is how chemical reactions allow to sense the modulated molecular concentrations from the environment and translate them into meaningful signals. So these were the question marks that we answered, and the model. And then we looked at attenuation of the end-to-end model, and like, you know, transmitter, propagation, and the receiver, and also the overall delay formula. And these are the model that we developed, the formulas. And for the channel model, we went to 1875 by Adolf Fix, right. So the Fix law 1 and 2, and we use that for our channel model, capturing this diffusion in the channel. Okay. So now next question was, after that, you know, this was a vanilla. There were no problems, noise, and all that stuff.
The population of molecules in the channel was a single population, uniform.
Uniform, yes. Homogeneous, right. That's right. You got it. That's why I use the word particle. The molecules were multiple. You jump into the more different cases. But anyhow, but it makes sense, you know, slow. Like here, in the next one was noises. So now, I believe that the noises are different than the classical noises. Okay. So now we said for the transmitter side, we call this particle sampling noise. Particle sampling is, these are continuous systems, right? The molecules are released. Now we need to somehow find discrete points to sample them. And sometimes we may miss on this sampling because of this decision, right? And then propagation side on the channel, it's called particle counting noise. So now we would do snapshots in the channel and say, oh, this many particles are there. Maybe that assumption is not correct, and you know, we may lose some of the information. And then the last one is, it's called chemical noises. On the receiver side, it's called ligand receptor kinetic noise. And that also we analyzed it. So the first two parts, the noises, we published in Transaction Signal Processing in June last year. And what we did is we developed and obtained variants of the noise as functions of transmit signal and its bandwidth, and also the design parameters. And then the last one was long enough, and I just skipped these to do time about particle sampling noise and particle counting noise. And the last one was the chemical ligand binding noises. It's not reproducing papers, by the way, so I don't need it in my age, but the first two noises were long enough, and then also this third one was long enough and also separate, so that's why we published in two different papers. Whereas in September 11, we studied this transaction signal processing, studied chemical reactions of the receiver, the ligand receptor kinetics noise. And then what we did, again, we obtained the variance of the noise as the function of the chemical parameters in terms of rates of binding and release reaction and the number of receptors at the receiver side. So now here's the picture that, you know, we are explaining the ligand binding process. That you know, ligand binding, as I told you, like the molecules are coming, these parts will be kind of binding, you know, sucking it, and sometimes it doesn't succeed, and then we lose them. And that's the kinetic noise we call it. Okay. And so now the next question was about, you know, capacity analysis. Can we rethink the entropy, for example? What is entropy here? And then accordingly redefine power consumption in molecular communication. So we did this work. How much time do I have? 10 minutes, 5 minutes, I'm over the time?
5 minutes.
Okay, yeah, 5 minutes. Oh, shoot, what time did we start, 11:10?
You can take that.
Yeah, so we had a little bit, okay. So I don't want to hold you here. So we did information capacity analysis, but interesting here is, that's why there is a guy, A. Ben Naim from Israel. He wrote a book about goodbye to information, the entropy with the thermodynamics. Here is we are mixing information theory and statistical mechanics, okay? In the information theory, we have quantification of information and communication channel. In statistical mechanics, we have thermodynamic behavior of the systems composed of a large number of particles. Here, and then entropy, energy, and then we have this physical reference model that we are looking at, which we did, and then we developed all these new capacity formulas. We published in Infocom last year, and so you see we combine information theory with thermodynamics, and then we calculated closed form expression for capacity as a function of bandwidth of the system, volume, temperature, and number of molecules and transmitted power. And of course, we use ideal gas because we want to find the theoretical maximum achievable information. Okay, so then what else is needed? Research challenges. We did all these things generically, like all these models that I developed. I presented to you. What will happen if we go to these specific cases, like molecular motors, calcium ions, bacteria, pheromones? Can we use our models? I don't think so, because they are generic and we need to do more detailed massage, but we can learn from those generic models. So we need to also analyze these separately, specific ones. And of course, all these issues that you said, heterogeneous like molecules, and then all these modulation techniques, new ones in the chemical domain. And then interference, we also did analysis of interference, by the way. We have the paper, but it's not publicly available now. Multiple users interacting on interferences, and then a bunch of these protocols that may be developed. And my fear is like many computer science people will take all these existing protocols and write tons of new papers. I hope they will not do it. Because taking AODV or DSR, whatever those, and writing them here, that will be fatal. Don't do that. So now the future will be, what we are doing is understanding these two domains from the communication perspective, like nanomaterial-based and biological, and then long-term, after 10 years, hopefully, the people will continue, and then we'll look at the hybrid cases too. And so we got, after a lot of, it says nice story, but we don't have time to tell you this. We got $3 million. That's the first time in my 30 years career I asked $3 million, I got $3 million from NASA. So they didn't have budget cuts. But 26th of June, they grilled me and my team, we are 5 professors, for 2 hours, tops of NSF. They had a bunch of questions, 2 hours long. One guy was advisor to the President Obama in nanoscale, and there was like the biology director, NSF director, assistant directors, like they were, Bill Trenter was there, like 10 of them, they were asking questions. And after 2 hours they said, we'll come back to you. And I couldn't sleep 3 days because I was in Barcelona. Will they give us or not? And finally they said, we'll give you the money, but I was thinking, budget cut, nothing. So $3 million with 5 professors with mechanical engineering and biology. And then we have this money, it's also $3 million, hopefully from the Department of Defense, granite that I told you the policies of Ken Paul from UT Dallas. And then we have these projects in N3 and quantum Molena and nanosimulation. This will be a good addition to the NS3, by the way, simulation for molecular communication. Then we started this workshop, IEEE workshop. Last year it was in Infocom. This year is in ICC in Ottawa. And they have good papers now. So then we have a Nano Networking Summit in Barcelona every summer in June. That is with some Juan Day that we go to parties after the summit. Yeah, the entire city is parties. I wish. Sure, yeah. I hope you know who messed some of them. Okay. And then I started the New Elsevier Journal 2 years ago. The idea came like many years ago, 3-4 years ago, but then we launched it in 2010. It's going really well. So I hope some of you will be inspired and start to do research. In fact, I have another activity now. You will say, wow, Samsung gave us money to study the drug delivery problems from the communication perspective. Samsung and that, right? So I had slides back at the time. So thank you again. I gave you this huge area that I could talk more and more. But if you're interested, go to our websites. And then the papers are there, information, and then I hope some of you will be interested to start to work on this. And don't be afraid of new areas. And I will close this section telling you a joke. In fact, it's a nice joke for all of us. It's also, we have those people. Like John, he's my host, and I can tell this because he's exactly on my side on that issue. I had friends, colleagues, 35 years ago, they were doing the same thing they're doing now. So the joke is, I mean, you did satellite and internet, that's why I can tell this, otherwise I wouldn't do it. So the joke is, a Greek old man comes to live with his father in New York. So he doesn't speak one word English. And you know, Mediterraneans want to be always independent, right? He hates to be always with his son. So he says, can you please teach me, say, coffee, bread, so that I can go and have my breakfast myself. So he teaches coffee, bread, and then, you know, so he's going every day, waiter, you know, coffee, bread, and the waiter is also understanding, you know. He brings always what he needs. After 1 month, he gets bored. He says, every day, coffee, bread. And then he says to the son, can you teach me tea and croissant? So, you know, tea, croissant, so he memorized everything. So he goes to the cafe, and today there is this one that he doesn't understand the foreigners, you know. He says, what do you want to have, sir? And then he says, proudly, you know, tea and croissant, and typical. What type of tea do you want to have? Black tea, vanilla tea, green tea, this. And then he says, what type of croissant? With chocolate, vanilla? He says, oh, coffee bread. So now, the story explains that very well, because I had colleagues, each time they come to a new domain. And it's not easy, guys. It took me many months, but it's exciting to understand, to learn, but then the payoff is more. But if you are afraid, you come here, you have some problems, like, you know, coffee bread, you go, you know, tea or croissant, you go back to your coffee bread. So you go back to your kin theory and you do kin theory stuff. That's not good. That's not good. Why? Of course I respect them. But the problem is, because there are thousands of papers there. Maybe you have fantastic, you know, solutions, but you don't get that much attention. And so it's better for young people, don't be scared to get into the new areas, but there are also these other extremes, right? They do everything. They do robotics, they do AI, they do mobile communication, they do real-time system. That's bullshit. I mean, they don't do that, because you're a wishy-washy man, you know, everything. But, you know, when you're a communication person, you move to new eras and new topics, and that's fine, like satellites, and like sensors and whatever, and you do similar things, it's fine. But don't do that way, you know, like I have colleagues, you know, they're a man of everything, you know, optical networks, you know, as I said, operating system, database, this and that, that's not good. So anyhow, these are some advice from me. Thank you.
Thank you for very inspiring talk. We have a little bit of time for one.
Sorry about the time, guys.
Any burning questions?
They are tired of they want to escape. Yes.
In your final example, when you're talking about the molecular communication, I think that you're using fictive transport for the description of the molecular transport. But when you talk about molecular transport at the nano scale, picking and diffusion starts to break down, becomes molecular diffusion.
Yes.
How are you reconciling?
That's what we did that work. Remember, I used the word fixed diffusion,
right.
Brownian motion behavior,
right.
And then we analyze it.
Well, those are actually two different things. I mean, picking diffusion is the macroscopic description
Yes.
of Brownian motion.
Yes, that's what our assumption is.
Okay.
But that needs to be more and more investigated.
Yeah.
Like all this nanoscale level behavior and the different types of molecules, and also their according diffusions. We are doing all this slowly. We are analyzing now under these assumptions, and as we learn more and more, we go deeper to those cases that we described.
I mean, you're right, and there's an additional question to what extent I can even talk about rates versus single bit communication models. So any other questions?
It's very interesting but complicated. If you want to jump immediately all those, it's very, very challenging. I mean, we want to understand from the communication perspective with these simplifying cases, and then learn as we go, and then fix our slides, and then like in the first paper, we don't have any noises. But if you had that solution for a normal channel propagation model, people say, "Are you stupid? Forget it," because there is no noise factor. But because it's new, with all these, transmitter behavior, receiver, and then diffusion, people accepted it. So that's why, because it's something new, there are novelties there. Maybe it's not exactly what's happening. It's a model. That's why we learn. And then we went to the noise and then the interferences. And slowly we go deeper and deeper.
So you have 3.5 hours to think more about all these provocative thoughts and come back at 3 to 4 for a round table. If you like to continue the discussion. Okay. So let's thank Ian again.
Thank you. Next time when I come back, there will be 5 people.